Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Chemistry Paper 2 from 2024. This paper is 1 hour 15 minutes long and it's tested on 4 main topics: the rate and extent of chemical reactions, organic chemistry, chemical analysis, chemistry of the atmosphere, and using resources. And this paper has 7 questions. So let's have a look at question number 1. Question number 1 is on the topic of chemistry of the atmosphere and using resources. The Earth's atmosphere has changed during the last 4.6 billion years. What is the approximate percentage of nitrogen and of oxygen in the Earth's atmosphere today? Draw one line from each gas. So draw one line from each gas to the percentage of that gas. So the percentage of nitrogen is the highest, which is about 80%. Oxygen is about 20%. So if you look in textbooks, you'll find that nitrogen is slightly stated as about 78%, oxygen is about 21%, and there's about 1% of other gases. Here they've just rounded up into higher percentages. Question 1.2. The approximate percentage of carbon dioxide in the Earth's early atmosphere was 95%. Which are 2 reasons why the percentage of carbon dioxide has decreased since the Earth's early atmosphere? Why did it actually decrease from 95%? Now, the current percentage of oxygen in the Earth's atmosphere is about 0.05%. It's really low. So, combustion of fuels actually increases the percentage of carbon dioxide. Deforestation actually means this carbon dioxide is left in the air. Dissolving in the oceans, yes, that's correct. Photosynthesis, yes, photosynthesis removes carbon dioxide from the air. Respiration actually does the opposite, which releases carbon dioxide into the air. Next question. Figure 1 shows the percentage in the change in the percentage of carbon dioxide in the Earth's atmosphere from 1800 to 2020. So as you can see, percentage of carbon dioxide in the Earth's atmosphere is 0.03%. And it relatively stays the same till about, well, the flat line is starting to change somewhere from there. And then it's slowly starting to increase up to 2020. Right now, there's 10 boxes between 50 years. So 50 divided by 10 is 5. So each box is 5 years here. Describe the trend in the percentage of carbon dioxide in the Earth's atmosphere from 1800 to 2020. Use data from figure 1. There's 3 marks there. So you could say we are trying to describe the trend from 1800 to, this is 65. So 1865. The carbon dioxide level is actually constant. It's not changing at about 0.03%. From there, it's slowly increasing to 0.04% up until 2020. Now, that's 4 boxes here. This is 2020. So how do you get the 3 marks? Right? From 1800, carbon dioxide percentage is constant. Right? You could say at 0.03% until 1850. So did I say 1850 there? Right? So they've actually included from there, right? So they're actually including it from here to increase. That's okay. Then increases 2, I'm going to change this to 0.0%, 0.04% by 2020. Next question. Carbon dioxide is a greenhouse gas. Which of the following is also a greenhouse gas? Now, argon, which is a noble gas, is not a greenhouse gas. Methane is. Nitrogen and oxygen are generally found in the Earth's atmosphere, so they are not greenhouse gases. Now, there's a couple of greenhouse gases, right? Mainly, which is carbon dioxide, right, which they have mentioned here, methane, and you could also include water vapor. Which of the following is an environmental problem caused by greenhouse gases? Now, acid rain is mainly caused by sulfur dioxide and nitrogen oxides. So, nitrogen oxide or nitrogen dioxide. So, it's not doesn't cause it's not a greenhouse gas. Climate change, yes. Global dimming is usually caused by soot. Next question. Calculate the relative formula mass of carbon dioxide. And they have given you carbon is 12 and oxygen is 16. So carbon is 12, oxygen O2, CO2. So that's 2 of them. So 2 times 16 is 32. So to that, you add this 12 from there for the carbon, and you get 44. Relative formula mass of carbon dioxide is 44 grams. That brings us to the end of question number 1. Let's have a look at question number 2. Question number 2 is on the topic of chemical analysis. Different tests can be used to identify chemicals. A student measured the melting points of 4 substances. Table 1 shows the results. So you have substance A, B, C, and D. Melting point of A is 52 degrees Celsius to 54. B is 61. C is -2 to 0. And D is 80 to 82. Which substance was pure? Give a reason for your answer. Now, the substance which is pure is B. Why? Because it has a very specific melting point. All substances, if it's pure, it should have a very single melting point. For example, ice freezes at 0, right? Anything above 0, it will melt. It boils at 100 degrees. But if you mix it with salt, that melting point or the boiling point of water actually changes. So it's the same for everything else, right? So the reason is, since it has a specific melting point. Next question. Anhydrous copper sulfate can be used to test for water. The word equation for the reaction is anhydrous copper sulfate plus water gives you hydrated copper sulfate. Complete the sentence. Choose the answers from the box. When water is added to anhydrous copper sulfate, the color changes from, now anhydrous means without the water. Hydrated means with the water. So anhydrous copper sulfate is actually white in color. And when you add water to it, it changes color from white to blue. The reaction between the anhydrous copper sulfate and water is reversible. How does the word equation show that the reaction is reversible? Now, this arrow, which is a double-headed arrow here, is the sign for a reversible reaction. So, you could simply draw the arrow right? Right? How does the word equation show that the reaction is reversible? Right? A double-headed arrow, double-headed arrow is used. OW. The formula of anhydrous copper sulfate is CuSO4. What is the total number of atoms in the formula CuSO4? So Cu is one atom, S is sulfur, and O4 means oxygen. There's four of them. So that's one copper, one sulfur, and four oxygen. That's a total of 6. Chlorine is a gas. Describe the test for chlorine. How do you test for chlorine? Now you could use a damp litmus paper, right? So litmus papers come in two colors. Either you get a red or a blue. And they're usually used commonly for testing acids and alkalis. But here you can actually use it for chlorine as well, right? So test gas with a damp, meaning that you dip it in water, damp, blue, or even red, it doesn't matter, red litmus paper. And what would you actually see as a result? The litmus paper turns white, or we say it's bleached. That brings us to the end of question number 2. Let's have a look at question number 3. Printer ink is a mixture of chemicals. So question number 3 is again on the chemical analysis topic. What is the name given to a mixture that has been designed for a useful product? Now, if we are actually designing it for a useful product like printer ink, it's called formulation. A student used chromatography to investigate the colors in a printer ink. So the solvent front is the line where the liquid that you're dipping the chromatography paper in is the solvent front. The starting line is right at the bottom here, and you've got two dots, red and blue. The student used a ruler for the start line. What would the student have used to draw the start line? Give one reason. Well, you use a pencil. Why would you use a pencil? Right? So that the start line does not dissolve in the solvent used, right? So if that ink from the start line actually dissolve, then it will actually mess up the chromatography paper as well. So you use a pencil because the pencil line doesn't dissolve in water or in alcohol, any other solvents. Determine the RF value of the red color. Use the equation distance moved by the color and distance moved by the solvent. So for this, you need to go back into looking at the image that they have given, and you will need a ruler for this. So make sure that you carry a ruler during exam, because this question is 4 marks worth. So first of all, let's measure the distance by the color and then by the solvents. How do you do it? That's for the red color. So what you would do is actually, right, you would measure up to the midpoint. So this line is actually already in the midpoint. So you'd measure the distance from there to there. using a ruler. And you would also measure the distance from the solvent front to the start line. Now, I measured this on a paper copy, and the distances that I found was 3.2 centimeters for the distance moved by the red color, 3.2 centimeters. Now, you can measure it in centimeters or millimeters, it doesn't matter, but the units have to be the same. And the distance moved by the solvent is 8 centimeters. So using the equation, RF equals 3.2 divided by 8, which gives me 0.4. Now, there is no unit for the RF value, it's just a number, and the maximum number you should get is 1, right? That's when the color and the solvent are actually in the same point, but you always should get less than 1 as your answer for RF values. If your answer is more than 1 or even 1, then you've done something wrong, generally. Table 2 shows the RF values for four blue colors. So you have the 4 different blue colors here and the RF values, and you can see they are all less than 1. The student determined that the RF value for the blue color in the printer ink was 0.86. So 0.86, which is very close to this color ration. Give one reason for your answer. Suggest which blue color was used. So it will be ration, PRUSSIAN, right? Reason, since the calculator, since the student's value is closest to 0.88. That brings us to the end of question number 3. Let's have a look at question number 4. Question number 4 is again on chemical analysis. Tap water must be safe to drink. What name is given to water that is safe to drink? And that name is potable water. Water that is safe to drink is known as potable water. Definitely not wastewater. Water is sterilized to make the water safe to drink. Which two of the following are used to sterilize water? So we don't use carbon dioxide, electrolysis. No, filtration is not to sterilize, it is to remove particles like sand and undissolved substances. Ozone, yes, ozone is a gas, right? We know of O2, which is oxygen. O2 is oxygen, right? O3 is ozone. And yes, we get O3 as well. And ultraviolet light is also used because ultraviolet light can kill bacteria. A student investigated the mass of dissolved solids in samples of river water, sea water, and tap water. So they're using 3 different samples of water. The method used was weigh an evaporating basin, measure 100 centimeter cube of river water, pour the river water into the evaporating basin, heat the evaporating basin until all the water has evaporated, weigh the evaporating basin and dissolved solids, calculate the mass of dissolved solids in the water, repeat steps 1 to 6 with seawater and then with tap water. So if I was to draw a really simple diagram, here's the evaporating basin and they're adding 100 ml of, what are they using? River water. And then you heat it till all the water evaporates off. And when it evaporates, what you're going to get is basically anything that was dissolved, other than the water is going to evaporate, all the dissolved particles is going to be left behind. So they're measuring an empty evaporating basin, and then they're measuring it again, which will contain the solids, and they're going to work out the difference to find the mass of the dissolved substance. Which is the most suitable equipment to measure 100 centimeter cube of water? A beaker is not that good. Conical flask, again, right? A beaker, remember, it's shaped like that. Conical flask is shaped like that. Oops, didn't want it to be a triangle. There you go. I thought it would actually disappear. There you go. Right. And a measuring cylinder is the best. And remember, measuring cylinders like that with the markings. Question 4.4. Table 3 shows the results. So you have the evaporating basin mass, and they are all not actually starting at the same mass, which is fine. Evaporating basin and dissolved solids, so you can see there is added mass here. Calculate the value x in table 3. So how are they calculating value x? They're literally finding out the difference between these two. So 114 minus 110.5, that gives me 3.5 grams. Identify the variables used in this investigation. Draw one line from each variable to the example of the variable. What is a control variable? Well, they are using only 100 centimeter cube of water. Mass of dissolved substance, that changes. Mass of the evaporating basin, that's actually changing as well. The room temperature, doesn't matter, they're going to heat it. Type of water, they're changing. The volume of water which is actually used, which is 100 centimeter cube. And the dependent is the mass of the dissolved substance. It depends on the type of water that you're actually using. Table 4 shows the mass of 4 masses of different types of ions dissolved in 1 decimeter cube, dm cube, of seawater. So 1 decimeter cube is 1,000 centimeter cube, or actually just 1 liter. So the calcium is 0.4, magnesium is 1.3, sulfate is 2.7. Complete figure 3. You should complete the scale for the y-axis, plot the data. So what have they given? They have given, figure 3 is a bar graph. Mass of iron dissolved in 1 decimeter cube. So it's starting at 0, and for these 10 boxes is 0.5. So the next would be here, which is 2, and that's 2.5. And let me write that properly. 2.5, and that would be 3. And they've done calcium, so we need to do the magnesium, which is 1.3, sulfate is 2.7, right? Magnesium, which is Mg, is 1.3, sulfate, I'll write as S, which is 2.7 on the side. So let me reduce the size of this so you can actually see all of this in. There you go. Right. So I'm going to use the width of the calcium column is only 5 boxes. So I'm going to add a column for magnesium ions. Magnesium should be 1.3. So now that's 1.5. Now between 1 and 1.5, halfway between is 1.25. So that will be just one more box above. here wanted. So there's 10 boxes between 0.5 divided by 10 is 0.05. So each box is 0.05. That's fine. Right. Let me do this properly. So I know this is 1.25, so the 1.3 is just one box above from there. Right. Let me bring that for there. There you go. And 2.7 should be 2.5, and then it should go up to, that's 4 boxes up, right? So this should be magnesium, and this is the sulfate. That brings us to the end of question number 4. And we had to use rulers, or you would have had to use rulers for 2 questions at the moment. So make sure that again have a ruler for the test. Let's have a look at the next question. Question number 5 is on chemistry of the atmosphere and using resources. I think this question is mainly about using resources. Life cycle assessments, LCAs, are used to assess the environmental impact of different products. 212 million kilograms of aluminium is used for packing in the UK each year. Wow, that's a lot. 68% of aluminium packing is recycled. Calculate the mass of aluminium packing that is recycled in the UK each year. So if I leave it as 200 in millions, right? So I want to find out what is 68% of 212 million, right? So what is 68% of 212? Well, if I divide 212 divided by 100, I would find out what is 1%, and then I multiply it by 68, and that would give me 144 million kilograms. Now they are asking the answer in million kilograms anyway, so I don't have to convert this 212 into millions. So it's 144 million kilogram is recycled. Drinks cans are made from aluminium. An aluminium can has a mass of 15.8 grams. 1,000 gram is equal to 1 kilogram. Calculate the whole number of aluminium cans that can be made from 4 kilogram of aluminium. Well, 4 kilogram, because 1 kilogram is equal to 1,000 grams, 4 kilogram, if I multiply that 4 by 1,000, it's equal to 4,000 grams. Now each aluminium can is 15.8 grams. So if I divide this by 15.8, I should get the whole number of cans. So what do I get if I divide 4,000 by 15.8? So let's do this in the calculator. 4,000 divided by 15.8. Remember, they want it in whole numbers. So 253.164. So 253.164. I'm not worried about the decimal place. I just need the whole number. So it will be 253 cans. Let's get rid of that. Question 5.3. Table 5 shows 3 methods used to dispose of wood and steel after use. So wood can be disposed of as waste, which means it's just simply chucked out, which winds up in the landfills, and we just literally bury it and forget about it. We can recycle it, or we can actually burn it. There's 3 different ways of getting rid of material that we don't actually use. Percentage of material disposed of by each method. So wood, 58% is thrown out as waste. 36% is recycled. So they might actually use it for other purpose, right? So instead of actually breaking any old tables, they might actually use it as old tables, such as 6% is burnt as wood. That's a pity. We could actually burn the rest of it, as rather than chucking it as waste, we can burn it, maybe to produce heat or electricity. Steel, 15% of it is disposed of as waste. So think about all the small little bits like paper clips and staple pins and all nuts and bolts, things that eventually get lost, right? So all the small items made of steel might actually be lost, hence it's 15%. 85% is actually recycled. That's good. Well, 0% is burned, obviously, because you can't burn steel. So evaluate, right? Evaluate means you need to use the information that is given here, and then you need to come up with your own reasoning at the end. The sustainability, right? What does sustainability mean? We'll come to that in a second. Of the disposal of wood and steel. So evaluate the sustainability. How long will it actually last if we keep on doing it? That relates to sustainability, right? The longer we can actually make something last, the longer we can say that it is sustainable, right? So looking at the information, right, we know that more steel is recycled. That means less is waste, right? Less is going to waste. And let me start with steel here, right? More steel, 85% of steel is recycled. Only 15% is going to waste. That means less is going into landfills. That means you're saving the landfill for other things. 0% is burnt, which means it's not contributing to global warming because it doesn't produce carbon dioxide, right? All of this are points that you can actually write down. What about wood? Well, for wood, right, bigger percentage of wood is actually going to waste compared to steel, right? 58% is actually going to waste. That means it's using more landfills, right? Less is actually recycled. That means we are going to have to cut down more trees if we want more wood, right? And 6% of it is burned. Now, although 6% is burnt wood, it still produces carbon dioxide, which contributes to global warming. So which is the best method, or which is more sustainable? The way that we are disposing of steel is more sustainable than wood, right? So we would actually want to change, or we would want to use less, waste less wood and recycle more of the wood, right? So here's a model answer for 4 marks, right? There's a lot of information here, so take some time to review it. More steel is recycled, right, which is about 85%, as I said, than wood, which is 36%. So less goes to waste, right? So less goes to waste, and less space is taken up in landfills, and less non-renewable resources are used. And I didn't mention about renewable or non-renewable before. And if we are actually recycling more, that means we are not using a lot of non-renewable resource. No steel is burned, so no carbon dioxide is produced, hence no contribution to climate change. More wood is disposed of as waste, so more space is taken up in landfills. Right? Although 6% of wood is disposed of by burning, it still produces carbon dioxide, which contributes to climate change. And steel is better disposed. So finally, steel is better disposed than wood, which needs to be recycled more, so less goes to waste. That brings us to the end of question number 5. Question number 6, which is on organic chemistry, is actually the same question that appears in the higher paper, which is in question 1 in the higher paper. And question number 7, which is on the rate and extent of chemical change, is question number 2 in the higher paper. So I'm going to make separate videos for the higher paper, so I suggest you watch the videos for the higher paper, question number 1 and 2. I'll put a link to the playlist and in the description for those videos when I do make them. Thanks for watching. If you found this video useful, always hit the like button and subscribe for more content. Thank you.